So next we're going to describe global linear models, and we'll focus on the three components of these models. So firstly we'll see that we have feature vectors. So f is going to be some function that actually maps an entire xy pair to some feature vector in some d-dimensional space. So x might, for example, be a sentence, and y might be a parse tree, for example. And so f will be a function that maps an input-output pair to a feature vector. Again, these feature vectors are going to be somewhat similar to the feature vectors you've seen in log linear models, but the difference is they now take in entire structures as their input. The second component is a function called gen, which takes an input x and maps the input to a set of candidates. So for example, we might take a sentence and we have some function that maps that sentence to a set of candidate possible parse trees for that sentence. And we'll see there are several ways of potentially doing this. Finally, we have a parameter vector v. That's the third component. This is also going to be in d dimensions, and we have the same number of parameters as we do features. And in general, the functions f and gen will be fixed, so they'll be defined ahead of time, and our training data will be used to set the parameter values v. And the parameters v are very similar to the kind of parameters we saw in log linear models. So let me talk about these three components in turn in a little more detail. So here's f. So again, sticking with the parsing problem, f takes an entire xy pair as input. So in the parsing case, we would have a sentence, which you can see at the fringe of this tree, paired with some parse tree. And we're going to define some function that takes this parse tree as input and returns a feature vector as output. So in this case, the dimensionality, d, the number of features, is equal to 1, 2, 3, 4, 5, 6, 7. So we have a 7-dimensional representation. In practice, in many of these models, d can be very large. You can often have tens of thousands or hundreds of thousands of features in these models, particularly in the parsing case if these features start to take into account lexical information, the identity of these individual words. F is going to play a critical role in that it defines how a candidate structure is represented. This is going to be the information which goes into the learning algorithm. This is going to be the information which the learning algorithm leverages in choosing between good and bad structures for a particular input. In general, we'll construct a feature vector by defining a number of individual features. So each feature is going to be some function that takes an entire structure as input and returns some real value as its output. A very common type of feature will be a feature which counts some kind of substructure within the structure we're looking at. So for the parsing case, for example, it would be very natural to define a feature which counts the number of times a particular rule, say A goes to BC, or S goes to NP-VP, or VP goes to VT-NP. Okay, so we could have a whole number of features which track counts of different rules in our grammar. So in this particular example, if I define hxy to be the number of times the rule A goes to BC is seen in the structure, for this particular tree we'll return the value 1, and for this tree we'll return the value 2, because we have two instances of this rule here and one instance of this rule here. So in general, we will define a feature vector by defining a whole set of functions. We'll actually have little d functions, h1 through hd, and we'll concatenate these to get a feature vector representation of a parse tree. So h1 might count the number of times the rule A goes to BC is seen within a tree, h2 might count the number of times some other rule is seen within the tree, and so on and so on. In fact, a very simple representation of parse trees would be to simply have one feature for every possible context-free rule in our underlying grammar. And so now you can see that one parse tree might get mapped to one feature vector, Another parse tree might get mapped to another feature vector like this. And again, I'll stress that these feature vector mappings are the input to the learning algorithm, so it's really important to come up with a good definition of these features. So the second component of global linear models is this function gen, which essentially takes an x as input and enumerates a set of candidate structures. And so the learning model is actually going to choose between one of these structures, but gen is critical in that it's going to enumerate the full set of candidates that is going to be considered for a particular input. So in the parsing case, gen would take a sentence as input and produce a set of candidate parse trees for that sentence. And we'll then see how we can use the feature vectors in combination with a parameter vector to choose between these different parse trees. So there are a number of different ways of defining gen. Here are a few. So for parsing, we could define gen x to be the set of all possible parses for x under a grammar, for example, a context-free grammar. And notice in this case, gen is large, because in general the number of parse trees for a sentence can easily grow exponentially with respect to the size of the sentence. Actually, later in this segment on global linear models, probably in next week's lectures, we will see ways of dealing with cases where gen x is a very large set like this one. Another scenario which is quite common within these models is to define gen x to be the top n most probable parses under a history-based model. So that means we can think of the history-based model as being a baseline approach, which for a given sentence will produce maybe 20 or 30 or 100 different parse trees. And so in this case, the size of gen is fairly manageable. It's a relatively small set. The motivation in this kind of setting is that the history-based model will do a pretty good job of generating 100 reasonably good parses, and in particular one of those parses may be the correct one, and then the global linear model will be used to select within these different parses using more powerful features than were seen in the underlying history-based model. In tagging, we could define gen x to be the set of all possible tag sequences for an input sentence. So if we have, say, the dog barks, and the set of tags we have is D and V, then we have basically every possible tag sequence as gen. Again, this set is quickly going to get very, very large. It's going to grow exponentially quickly with respect to the length of the sentence. And finally, in a translation setting, gen x might be the set of all possible English translations for some French sentence, maybe all possible translations, for example, under a phrase-based lexicon with some particular distortion limit. But abstractly, the important thing to remember is that gen, in general, is some way we have of enumerating a set of candidates for an input sentence x. The final component of global linear models is the parameter vector, and this is what is going to be actually learned from the training examples. So I'll use little v to refer to a parameter vector, which is also in d dimensions. Remember that the feature vector has d features. And we'll use f and v together to map a candidate structure to a real valued score. So if we take some xy pair, in this case it's a sentence paired with a parse tree, we can first map that structure to a feature vector through this function f. And then secondly, we can take the inner product between f and v, the dot product, in exactly the same way as we saw for log linear models, to get an overall score for the parse tree. So here we have the feature vector f, and here I have a parameter vector which says, for example, that the first feature gets weight 1.9, the second has weight minus 0.3, third has 0.2, and so on and so on. I take the inner product of these two vectors, I get some score, for example 5.8 in this particular example. Now this score is going to have an interpretation as being some measure of the plausibility of this particular structure y when paired with x. More likely structures are going to have higher scores. And in particular, we'll see soon that the output from the global linear model will be the structure y that maximizes this inner product. So again, I want to stress that we've made a rather radical move here. We've basically taken the technology we saw with log linear models, but now applied it to entire structures. So now an entire parse structure gets mapped through some feature vector to some feature vector representation. And then the entire parse structure gets a score, which is the inner product of f and v. And this score is essentially going to replace what we'd seen in other models in this class, which was either a joint probability of y and x or a conditional probability of y given x. We'll see that this score, this inner product, plays a rather similar role to these probabilities. Now that I've given you these three parts to the model, we can put things together and see how the global linear model defines a function f from the set of inputs to the set of outputs y. So what is this function capital F? So this is going to take some input x and it's going to return some structure y, and that calculation is actually very simple. We simply search for the y in the set of candidates gen x that maximizes the score I showed you on the previous slide. And so it's really a very simple idea. We simply choose the highest scoring candidate as the most plausible structure. So this critically is how our function from inputs to outputs is defined. And you can see it depends on all three components, on gen, on f, and v. Now, as I said before, gen and f will in general be fixed. They'll be chosen before we see the training examples. A critical question we'll address is that given training examples xi, yi for I equals 1 to n, so given examples of the xy mapping, how do we set these parameters v? And this is something we'll come to shortly. So this slide may help us to visualize the entire process a little bit better. We have some input sentence, and we want to map that to a parse tree. This function gen first enumerates some set of candidate parse trees for this input sentence. In this case, there are 1, 2, 3, 4, 5, 6 possible parse trees. Each of these parse trees gets mapped to a different feature vector through the function f. So we have 1, 2, 3, 4, 5, 6 feature vectors, one for each of these parse trees. And then given a parameter vector v, we can take the inner product of f and v to give a score for each of these different parse trees. So we have 1, 2, 3, 4, 5, 6 scores. So this tree gets score 13.6, this tree gets score 12.2, 12.1, 3.3, 9.4, 11.1. And then finally, we find the highest scoring parse tree. So 13.6 is the highest of these scores. So this parse tree is actually selected as the output of the model. So this argmax operation picks the highest scoring tree. You can see that as you vary these parameter values v, you're going to affect the scores given to these different parse trees, and you're going to affect the ranking given to these different parse trees, and most importantly, you're going to affect the final output of the model, this argmax. So the training procedure is essentially going to somehow manipulate these parameters in a way that we do well in recovering the structures on these on our training or test examples.